Welcome to our November Saturday morning Astro at Purdue. Our topic this morning actually may be familiar to some of you and very familiar to one of you, the expanding universe. We're going to take a look at Doppler shift and how we use light to measure things going on in our universe, particularly the expansion of the universe. We're just going to dive right in. I'm Dave Cedarberg. I'm the outreach coordinator for Purdue Physics and Astronomy. And we have with us this morning Professor Dimitrios. The experiment we're going to do is actually based on using sound, but the principles are the same. The equations are the same. The math is the same for what astronomers do to calculate the expansion of the universe, how far away galaxies are, and how fast they're moving. So with that said, I'm going to share my screen. We're going to ask what you think about light. And let me start the poll. Okay, so the question is here, select the statements about sound that you think are true. Make your choices, select the ones that you think are true, and we'll see what you think about sound before we talk about light. Choice one, sound is an energy carrying wave. That's a true statement. Sound is a form of energy. It is caused by vibration of materials, whether those materials are air, water, liquid, gas, solid. Sound is transmitted through those materials. Who can tell me, either unmute yourself or put in chat, how sound travels from within a material? How does sound get from one point to another? Who can explain that? Who's got an idea? Samuel says it takes a medium. It needs a medium. It travels in waves. Those are both true. So it's caused by vibrations of molecules within the material. So in air, for example, the molecules vibrate one to the other. Good answers. And of course, since there is no medium in deep space, sound doesn't travel in space. Good answers. Let's see, frequency changes. The frequency you hear changes with motion. That is true. We've got, the slide on the screen that shows a little creature with a fire truck. When a siren comes by, you all are all familiar with that, I'm sure. The frequency of the sound changes. Number three, frequency refers to how loud a sound is. That actually is not a true statement. Frequency refers to pitch. So, and that's also related to wavelength. If you want to talk about sound, then that would be called amplitude. Amplitude is how loud a sound is. And the last one, frequency is the same as pitch. And that is a true statement. Frequency and pitch are true. How high and how low a sound is. There were the poll questions. There are the correct answers, A, B, and D. Let's move forward. So we're going to do a breakout. And before we do that, one of the things that we asked you to do was to download an app called Phyphox. So you're going to need two things if you want to do the experiment. And if you didn't do that, that's okay. You can either do it now or watch what other people do. That's no problem. Any problems, speak up, tell me you're okay, give me a thumbs up, give me an emoji or something, put it in chat. If you have a problem, let us know. We're going to continue to move on and we'll address your questions as we need to. The other thing you'll need is another device, a laptop, a tablet, or a PC that has a sound generator. We need to generate a sound, a continuous tone, so we can do an experiment with that tone. And we'll tell you what frequency to use here in a minute. I'm going to show you a couple slides before we go to breakout, and then we'll have you do the experiment in breakout. So the first thing I want you to see, we've talked about Phyphox, so I don't think we need that. On the left side of your screen, you see when you open Phyphox, you'll have all kinds of options. This is a really cool app. If you're into anything science, You can do all kinds of experiments with Phyphox. I've highlighted in yellow with the yellow box, the Doppler effect. That's the experiment that we're going to do. And when you click Doppler effect, you get the image in the middle. You see three things in yellow boxes: setup with results, base frequency, and an arrow that means start and stop. We're going to use a base frequency of 1000. The other things on this screen, the other things under base frequency, do not matter for us. Those are things we don't have to change. Once you run your experiment, you'll just hit the yellow arrow. Once you run the experiment, you'll click results, and the TAs will go over what to do with your data. A couple of things that you want to know beforehand. This is a sound sensitive experiment, so extra noises, little brothers and sisters and dogs and things are going to have an effect on your results. So you'd like to be as quiet as possible, no talking during the experiment. I think the other things, the TAs will go with you in the breakout, so I probably don't need to go through that entire list. So let's move to the next slide and see if we're ready to go. All right, let's go to breakouts.
Should be able to, from that link that I just put in the chat, can you see that?
Yeah, I can.
Okay, so when you go there, it's going to just pull up the tone generator and you'll just move the slider up to 1000. That's the frequency that we're going to be starting at.
Okay, thank you.
Yep, all right. So just a reminder, be in a really, really quiet environment. You don't want any added background noise contributing to your data. And you want to make sure that when you move your phone, you move it at a speed that's constant. It should just be the same speed going back and forth towards your whatever device is playing the sound.
Dylan, since they haven't seen this done, why don't you just give a quick demo on what that will look like?
Yeah, so when you open Phyphox, you're going to go to the acoustics tab that says Doppler effect. I don't know if you can see it. It should be down in here. And it'll pull up that screen that Dave showed where it has the parameters with Doppler effect. It's got the base frequency, and we want to make sure that's set to 1000. And then on that link that I put in the chat, that's just a regular tone generator on whatever device you're going to be doing this on. And you want to make sure that's at 1000 hertz. So it should look like this at 1000 hertz. I'm going to play it really briefly. I don't want it to be too loud. And it should sound like that.
Play it again.
Okay. And then while that's playing, and you have your Phyphox pulled up on Doppler or on your phone, when you hit the play button, I don't know, it should be up on that side, that little arrow, and it'll turn into the two bars showing that it's playing. You'll start the sound and you'll move your phone back and forth towards whatever other device you have. I have an iPad in my hand, so it would be moving it back and forth at a constant speed.
What the idea will be, I would hold your phone so that the microphone is not behind your hand. I would hold it looking like this. So we have, this is going to be the detector, the observer, the PC or your tone generator station will be the source. And so start the source, start Phyphox, and go back and forth like this in a constant motion, and do that about 10 or 15 times without talking, of course. And then hit stop, and then we'll look at your data. So we'll give you a few minutes to go ahead and do that.
Yep, that's a much better explanation. Thanks, Dave.
Well, I've explained it before.
Yeah, that's right. Looks like we have a few people done. Do you think, Dave, it would be better if I just pulled up the sample one that we had to show what it should look like?
Yes, that'd be great.
Yeah, okay. Okay, can you see that? Took me a second. Okay, so this is a some sample data that we had from before. Now this one's at 800 hertz, yours should be at 1,000. But you want to take note of your highest frequency and the lowest frequency you get. Your highest frequency is going to be as you're moving your phone or whatever you have Phyphox on towards the device that's playing the sound, towards the sound. It records it as a higher frequency. And as you move away, you'll see this downward. So I don't know if you guys can see my cursor, but this downward motion as it moves away, it's going to record as a lower frequency. And you should have data that looks like this. Now you can zoom in and play around a little bit. It probably is, it looks a little bit different than that. Does anybody see anything like that has it done so far?
Dylan?
Yeah.
I'm going, if you will stop sharing for a minute, the screen.
Yeah, go ahead.
I'm going to show everybody. So your data, the data you collected is not going to look very neat. So what you're going to need to do, you're going to want to select the frequency data, and you're going to need to expand and contract and try and bring that into what looks like a reasonable pattern. Now, this isn't a very good pattern because I just did this on the fly just now, but in fact, it's really pretty crummy. But by massaging, by expanding and contracting the screen a little bit, you want to try and get a recognizable, repetitive pattern. So you see what I'm doing? I'm just taking my fingers and grabbing the screen and stretching and shrinking. Okay, Dylan, bring that slide back up again. So what you want to gain from this point, from this graph, is look for your 1,000, your base frequency, and then see where the peaks are above and where the troughs are below. How high up does the graph go from the base frequency, and then how low? And experience shows us that it should be maybe about 5 or 10 hertz, or 5 or 10 cycles per second. So if your base frequency is 1,000, I would expect the highest frequency to be maybe 1,010 or 1,015, probably somewhere in that range. So I'd be interested to know, and pop it in chat. Let's see what kind of answers you got.
For my highest, I got around 1,008, and then for the lowest, I got 995.
Perfect. No, that's great. That's well within the range that that we'd be looking for. So let me ask what that means. Is the frequency higher when you're moving the phone toward the sound source, or is it higher when you're moving away? It's not an easy question maybe to answer. You guys are getting good results so far. And if you're not getting good results, that's okay. You can use the data from someone else in the breakout group. It's fine. Okay, Dylan, what's next? Are we going to calculate? What are we going to do? We need to identify the source frequency. So for everybody, that's going to be 1,000.
Right, source frequency is 1,000.
And then we want the frequency moving away.
Right.
So is that going to be the highest frequency or the lowest frequency, Dylan?
That's going to be the lower one. And when it's moving towards, it's going to be the highest one. And I think somebody in the chat, I believe it was Alvina, hit that right on the head.
Okay. Our next step will be what? To calculate the wavelength of each frequency?
Yes.
So that's going to be slide 13, if you want to show everybody.
All right.
Let me just answer Myra's question. We want to know the next step. which is going to be calculating. See, so you've got a frequency. That's you all have frequencies. That's great. You have like 1,000 for your base, and then a lower frequency moving away, which might be 998 or 990 or something like that. We want to calculate the wavelength. So the frequency is how fast it's vibrating. The wavelength is the distance between those vibrations.
Yeah, but what you'll want to do is you want to take those highest lowest, and you're going to want to calculate the wavelength. And you have your source frequency, which for everybody is going to be 1,000. And then for this portion, we'll just do the moving away frequency. So as you're moving away, it's going to be the lower frequency. So you have this equation right here where you have wavelength, which is lambda, equals to the speed of sound divided by the frequency. And to calculate it for your source, it's just divided by 1,000 hertz or cycles per second. And your observed value in this case is going to be whatever your lowest value is. So for you, Myra, it'd be 995. And those are going to be your wavelength for your source and the wavelength for your phone as it was moving away. Or yeah.
So for everybody, the wavelength of the source, speed of sound divided by 1,000, is going to just be 0.34 meters. So I think that's pretty interesting. The wavelength of a sound wave is about 1/3 of a meter. I think that's a surprise for most of us. Then to do the same thing, or if your frequency moving away is, let's say 990, then you'll do the same thing. 340 divided by 990.
And you should notice that it's not going to be a very big difference, but there is going to be a difference.
Yeah, it's not. So the first one is 0.340, and for 990, 0.343. 3 digits is enough.
Anybody having any trouble with this part?
Yeah, let's pause here to see.
Anybody have any questions, or anybody want to share what values they got for theirs?
Hey, Dave.
Hey, Ethan, I'm going to just jump in for a minute. Where are you now, and what you need to do?
Everyone's taken. Yes, everyone's done the experiment. Just sort of introducing them to what's in the slides upcoming ahead.
Okay, so everyone has a base wavelength. I'm sorry, everyone has a base frequency, and they've looked at their graph that have identified. Okay, so next step is what? To calculate the wavelength?
Yes.
Okay.
I introduced that to them already.
Okay.
The observed wavelength is equal to speed of sound over the observed frequency.
Okay, let's see what answers they get.
Okay.
So you all have your source frequency. For everybody, that's 1,000. Your frequency moving away should be something like 995, 990, 996, something a little less than 1,000. You're going to take those two numbers, use the equation below to calculate the wavelength. Ethan, look at you, Mr. Fancy, writing on the screen.
So you guys are going to take that speed of sound value that you see there, 340 meters per second, and divide by the frequencies that you guys observed. So the maximum frequency and the source frequency and the frequency moving away.
We have about 5 minutes, so we'll need to get the wavelengths and then go to the next slide and calculate I think that's going to be the velocity, isn't it?
So everyone can see here, I did, this is the calculation for the source wavelength, which is your tone generator at 1,000 hertz. A hertz, for a reminder, or if anyone doesn't know, is 1/seconds. So so this would be 998 per second. So these seconds cancel out, and you will get the wavelength is 0.34 meters.
Samuel, you are correct. Your comment about them being very close to the same. Samuel, I have a question for you. What would make them be more different? What would cause a greater difference between the wavelengths in terms of moving the phone? What would you do to move the phone to make the difference greater? Do you have an idea?
Maybe like not, I don't know, like if I start like moving my cell phone this far, like I would increase the distance between the source and the waveform, like between the source and my cell phone.
Would you think, so the wavelengths are, the frequency, when you're moving away, the frequency is less, and you already see that that's a longer wavelength. What would you do? How would you move the phone to stretch the waves even more to make the wavelength longer still? Would you move it?
I will move it faster.
You are correct. Yes. So since we're moving the phone fairly slowly, that's why the difference is pretty small. If you were to move the phone faster, then that difference would be greater and the wavelength would be even longer. Ethan, Amelia, can we jump to calculating the next slide and calculate the velocity of the phone?
Yep. Can do.
I'm going to jump to the other breakout room.
Got it.
We've got about 4 minutes to finish up. So if we
4
can,
minutes, perfect. I think we've actually gotten through it.
okay.
Unless there was something that I forgot to do, which is quite possible today.
So we're going to take the speed of sound
Mhm.
times the difference between moving away and the source. So moving away, let's see, for everyone, that's going to be different for everyone. I'm going to take a number like 0.343 minus the source. And for everybody, the source is the same, 0.340. Divide by the source, 0.340. You know, these are units of meters.
Yep, and then what you should find in all these units of meters, if you were interested in the dimensional analysis, is you have meters minus meters is still meters, divided by meters will cancel out the meters, and you'll be left with meters per second, which is velocity for your phone.
Okay,
And
can we get an answer? Can we calculate that answer? Does somebody have an answer?
we actually did. We had Sawyer got 2, Alvina got 2, and I believe Myra put in, she got 1.7, and Nelly got 3.
Okay,
From what people have shared with me so far.
okay. All right, I'm going to close the breakout rooms.
Perfect.
And we're going to dash back. Okay, I think everybody is back. So Ethan, go ahead. I'll give you 2 minutes.
Okay, great.
Bring that slide up.
What's something new that everyone learned today with this? Like, have you learned something new? Let's start there. What's something that's interested you today?
Anybody have something they found out that they didn't know before? Ethan, they're all spellbound, I think. So Sawyer said calculating the velocity of the phone. And Nellie said everything has been, for me today, I've never focused on any of these topics before. I think it's pretty cool to calculate the velocity of the phone from the data you collected. I think that is just super fantastic. The reason I think that's fantastic is because what you did just now is the same method, the same mathematics, and the same approach that astronomers use to calculate how fast galaxies are moving away. That is the whole point of today. So you guys did really well. That's a great observation. You learned a little bit about Greek letters. We learned what lambda is. So lambda is just a Greek letter for L, and L means the wavelength, like L length. So I think you are doing well. Ethan, ask these 3 questions real quickly.
Okay, so we'll start with what if the source, in this instance, a truck moving towards the man, was moving faster? Now you can see there's a diagram right here that is representing the fire truck moving towards it. But can anyone describe what's going on in this image? What's happening to the wavelength?
So if the truck moved faster, what would happen? What would happen to the wavelength? Let's say it's moving faster toward the man. If it's moving faster toward the man, what would happen to the wavelength? It's shortening. Okay, Hannah, good answer. Ethan, next question.
Okay, what if the source, the truck in this case, was stationary and you ran towards it? So now you are running towards the stationary source, the truck. What's going to happen there? Is the wavelength going to change? The source isn't moving. What would happen in this instance? The same thing will occur. Since you are the one moving, the wavelength is still going to shorten. Now it's not going to, perhaps it's not going to be, it's not going to shorten as much as if the truck was moving, because the truck is faster, but it is still compressing. Now, let's move on to the 3rd question. Where would you hear the true frequency of the siren? Now, in our instance, when we were in our experiment, we were talking about the tone generator that was at 1,000 hertz. How would you hear the true frequency?
So Daniel, I think the question would be, the man is standing still. The truck is moving. Where in the path of the truck would the frequency be the true frequency of the siren? That is a tricky question. In the truck. Good answer. Good answer. So if you were in the truck, it would be the same. If the truck also, if you were standing on the sidewalk and the truck was passing by, the true frequency you would hear would be where the truck was actually exactly opposite to you. It's not approaching, it's not moving away, it's exactly perpendicular to where you're standing. Then also it would be the same frequency.
Samuel has a great elaboration on that. It's the relative speed of the truck needs to be 0. So as was mentioned before, or as he mentioned before, if you are moving, let's say to the left right here at the same speed as the truck, the speed between you two is 0. So that'll also be the true frequency.
Okay, Ethan, thank you. I got to just compliment our students. You guys are right on the money here. I am very impressed. Ethan, stop sharing, and we're going to move on. I need to turn things over. Again, I just want to thank the students for doing so well. You learned a few things. I think you appreciate the magnitude of what we're about to do next. And that is talk about the speed of galaxies and the expansion of the universe. And for that, I'd like to introduce Professor Dimitrios. So Dimitrios, we are running over on time. We wanted to be about, to this point, 15 minutes ago, but it's okay. Let's just move ahead and we'll be a little over. And if somebody has to leave, that's fine. Any of the students can leave whenever they want to, but I would like to get professors to talk to you. So, all right, Dimitrios.
Hello, everybody. I'm so happy to be here, actually. It's very exciting to see all these young people, inquiring minds. As Dave said, and I have the same feeling. I don't have much to share with you because you have already figured out the basics, how this thing works, how the Doppler effect works. I'm an astrophysicist, a professor here at Purdue. And I'm interested in studying black holes, which actually they are not so black, it's a misnomer. They are some of the brightest objects in the universe, produce a lot of light. And in fact, I got I got motivated to study these objects quite some time ago when I was about your age. So you being inquiring minds, maybe you will be interested to study physics or science in general in the future. But definitely by being here in this activity, you are taking the right steps towards learning all about our cosmos. Now, I'll share with you the screen and let's discuss about light. So far, we have discussed about sound. And that's what we can hear because of the atmosphere of the Earth. Now, when we want to understand the universe, there is vacuum, there is no sound coming from the universe, but there is light coming. And by studying the light, we can tell all about the galaxies and the stars out there. But now, speaking about light, let's think a bit. What can we learn by just looking at the light about, say, stars or galaxies or the universe in total? And now I will leave it to Dave to start a new poll, which has the following question. Now, from the colors of the light from a galaxy, from a distant galaxy, what can we learn? So I'll leave it for a few minutes for you to tell me. More than one actual answers can be correct.
Okay, so the poll is live. Some of you are already entering your answers. You want to select as many of the statements as you think are correct. I'll give you about 10 more seconds.
So,
all right, I'm going to close the poll. Dimitrios, we have a good selection of answers. I will let you go over the correct responses.
okay, I see here we have a winner for how far away this galaxy is. 88% of you said that we can learn that. Then second is what elements it is composed of. And then half and half, we were kind of undecided if we can learn of how fast and if the galaxy is moving towards or away from us. Well, the correct answer is actually that it's all of the above. Let me see if I can. Okay, here it's all of the above is true. In fact, by studying the light from a galaxy, we can learn much information about the galaxy, the composition, the velocity with which the galaxy is moving towards or away from us, and we can actually learn something about the distance to this galaxy. So let's see how these things happen. Well, we have already, let's see, can I remove this poll? Okay, I have this poll image. Okay, get rid of it. How do we learn about velocity? In fact, the effect is very similar to what we studied already about sound. If a source of light moves towards us, we see the Doppler effect, a change in the wavelength. there is a formula very similar to what you have already learned so far in this activity with the phone. Here we have the formula that you applied actually to calculate the velocity of the phone relative to the source of the sound. Now, a very similar formula applies to light, and the only difference here is that we don't have the speed of sound, c sub s, but we have the speed of light. Light is much faster, of course, than sound. In fact, it's about 1 million times faster. And in 1 second, actually, the light covers a distance of 300 million meters. But the formula is exactly the same. With that formula, you can measure the velocity of an object relative to us. And I have a question, please.
Yes, Professor, I got a question. Because we are talking about light, shouldn't we take into account special relativity?
Of course, we should take into account special relativity, and what a great question. In fact, this formula here for the Doppler effect does not contain corrections because of special relativity. This formula is applicable for lower velocities of the galaxy. But what a great question. In fact, that's absolutely correct. So in the simple case of relatively slow motion, this is the applicable formula. So with this formula, we can actually calculate the relative velocity of an object relatively to us by measuring the wavelengths. Now, just as it happened with the sound, when a source is moving away from us, what do you think happens to the wavelength of the light? What was happening with the sound?
Light would get like redshifting.
Well, once a source moves away from you, the wavelength gets stretched, and then you get a redshift. When a source moves towards us, then the wavelength of the light gets squeezed, gets shorter, and you get the so-called blue shift. And since we are talking about colors, red and blue, just like sound has its pitch, which is related to the wavelength, light has its own colors. Here, I give you a picture of how colors could look like from the sun. From the sun, you get red color, you get yellow, green, up to violet color. What do you think is the difference between a red color light and a blue color light? Is the difference in the speed with which they propagate, or is there a difference in their wavelength? We have some answers in the chat, or I cannot see the chat.
We have one answer in chat that says wavelength.
That is correct. Just look at the picture here. I have the red photon, which has the very long wavelength, and then progressively we go to shorter and shorter wavelengths when we move through the colors of the rainbow, until we make it to the violet, which has the shortest wavelengths. So red is long wavelength, and the blue or violet is the shortest wavelengths that our eyes can see. Now, by looking at this spectrum, at all the colors we have access to, we can study galaxies. And here I give you an example of the spectrum we get from a galaxy. Now, in this spectrum, you do see all the different colors. The galaxy produces light in all the different colors, but you also see something else in this spectrum. Can someone comment on what is special about this rainbow here? Is it a smooth light moving smoothly from the red to the blue, or there is something happening? Any thoughts here? For example, what is this thing in the middle? If you can see the mouse here, there are some dark spots here on this spectrum. Here are specific wavelengths or frequencies where the galaxy is not shining. These are called absorption lines. These are part of the spectrum where we don't get light from the galaxy. In fact, this tells us about the composition of the galaxy, tells us about the molecules and the atoms that are there in the galaxy. Now, if this is our own galaxy, the spectrum would look like this, as in this example I have here. You have different lines where you don't get line. However, in another case of a galaxy, you can get a different spectrum. Let's compare the two spectra of these two different galaxies. Do you notice any differences? Where are the lines in one? And if you can see some change in the dark spots in the lines in the other galaxy. Do we have some answers in the chat? I believe.
Yes, we do. We have somebody that says Sawyer, moving away has longer wavelengths. The lines moved toward the left. I guess that depends relative to which one you're looking at.
Yes.
But yes, the lines, yes, those are
correct. So let's see. All the lines systematically move in one direction if you compare the two galaxies. For example, you get these few lines that have moved to the right when the galaxy is moving away from us. This big line here moved again by the same amount to the right. When a galaxy moves with respect to us, all the lines are shifting, and the change in the wavelength gives us the redshift of the galaxy, which can also be used to measure the velocity of the galaxy with respect to us. Now, when you get a redshift, when you get the wavelengths to get longer, then the galaxy is moving away from us. When the galaxy is approaching us, you get a blue shift, you get all the lines to move to the bluer part of the electromagnetic spectrum. Now, let's see an example. Suppose that you are observing with your telescope, looking at a galaxy, and you see a specific line. At the source, at the galaxy, you know that this line is at 393 nanometers. Here, just to stress the units, wavelengths in the optical light are measured in units of 10 to the minus 9th meters, which is nanometers. Okay, but pay attention to the main number here, which is 393.3 nanometers. That is the wavelength of the line at the source. But then we are observing this line at 401 nanometers. Okay, the question is, can we tell whether the galaxy is approaching or moving away from us?
Yes, we can.
Yes, we can. That's the spirit. So what is happening there?
So I think that if the difference between them is negative, that means like it's moving towards us. And if the difference is positive, then the source is moving away from us.
Correct. In this case, what is happening? The observed wavelength is longer than the source, that of the source. And when do we get the stretching of the wavelength? When the source is moving away from us, correct? So the observed wavelength is longer, we get a redshift, and indeed, this source is moving away from us. Not only that, we can not only tell that it's moving away, but we can tell also how fast it's moving away from us. All we need to do is apply the Doppler formula that we have learned already. In that case, the velocity of the galaxy is given by the speed of light times the redshift z, but this ratio of the wavelengths that we have already discussed. Now, I will show you how this, an example how this calculation takes place in practice. All we need here is to substitute the two wavelengths. the numbers we are having over here, and be a bit brave, not to panic because of this 10 to the minus 9th meters, this large or very small number there. We don't panic because these numbers drop out of the calculation. They simplify in the fraction. As you see here, both sides of the fraction has this 10 to the minus 9 meters. In reality, all you have to do is subtract the main numbers, 401 minus 393, and in the denominator, keep the 393. The 10 to the minus 9th meters drops out. And here we still have c, which is the speed of light. Now, if you calculate this quantity here, you find that the velocity of this galaxy in the specific example is 6,480 kilometers per second moving away from us. This is a very typical case. Actually, it's a relatively slow moving galaxy, but think about this for a second. Every second, this galaxy moves away from us by over 6,000 kilometers. That's the radius of the Earth. This galaxy, every second that passes, runs away from us at a huge speed. Now, let's see one more example quite fast to how this technique is applying again. So you are again astronomer, you are looking at another galaxy. And in that case, the source wavelength is at 600. I have a hand here. Please, Samuel.
Professor, I noticed something that like the redshift must be like less than 1. What happens like when it is like 1 or greater than 1? Like how can I understand that?
Well, Samuel, I cannot hide anything from you. So look, as you asked before, relativity, the special theory of relativity plays a role. And this expression I gave you for the redshift is correct when we are talking about velocities that are much smaller than the speed of light. If galaxies move much smaller at speeds much lower than the speed of light. When a galaxy is very far away, when the redshift becomes more than 1, in that case, you have to use the correct relativistic expression for the redshift. In that case, the speed of the galaxy remains less than the speed of light, but correctly, as you said, you can have objects with redshift more than 1. That was an excellent question. Okay, let's look at this second case we are talking about here. In this case, the observed wavelength of the galaxy is 656.1 nanometers, while the source wavelength of this galaxy is 656.3. And the question is this galaxy moving towards us or away from us? Now the difference is very small between the two wavelengths, but there is still a difference, and that is important.
We have one comment in the chat that says it is moving towards us.
And that is quite correct. Notice that the observed wavelength now is shorter than what the source is producing. The galaxy is indeed coming towards us. It's an exceptional galaxy. It's a rarity because most of the galaxies are actually moving away from us. And it's actually a nearby large galaxy. Let's put its photo there and try to identify this galaxy. Do we know who this galaxy is by name?
Andromeda.
Well, it's Andromeda galaxy, correctly. It's one large galaxy in our neighborhood, and in fact, it's coming towards us at some high speed, approaching us, and maybe coming to collide with our own galaxy in several billion years. So we still have some time to study and enjoy Andromeda, but it looks quite menacing at this point. Okay, now we have understood that we have a technique to measure the velocity, the speed of galaxies. And of course, some 100 years ago, Hubble decided to do this in a systematic way. He looked at a dozen of galaxies, or a few dozen of galaxies, and he could measure the distance to these galaxies and their velocity. And having this information, you can make a plot where each galaxy is one point, and one axis measures distance, and the other axis measures velocity. And to his big surprise, he found the following, and I'm giving you here his plot from 100 years ago, or what approximately he found. Here you see red points, these are the galaxies, distance in some astronomers' units, and velocity. Positive velocities correspond to galaxies that move away from us. Negative velocities would be galaxies that move towards us. In these examples that Hubble had, all the galaxies were actually doing what? They are characterized by positive velocities.
Moving away from us.
All the galaxies that he studied, besides Andromeda, were moving away from us. That was a great surprise. Now, what else do you notice about this plot that Hubble produced? Are the red points having a trend, or are random? What happens, for example, to the red points when the distance increases? What happens to the velocity of the galaxies when the distance increases, when we move to the right of this plot?
It increases as well.
Okay, so you see, when the distance increases, the velocity also increases. Not only that all the galaxies are moving away from us, but the further away a galaxy, the faster it moves away from us. Actually, our universe is expanding. And you can nicely see the expansion of the universe, in fact, with, well, by inflating balloons. So, Dave, do you think we have time to inflate some balloons?
Amelia, can you quickly, like in 1 minute, show us your demonstration?
Yep. Okay. So
Dimitrios, why don't you'll have to unshare your screen for a minute.
Oh, yes.
Okay, Amelia, show us what you've got.
all right.
Some of you may have a balloon, but that's okay. Just Amelia will do this for you.
just watch what I do real quick. So these galaxies are moving away from us because the universe is expanding. So let's pretend that this balloon is space. The outside of this balloon represents space. And right now, I'm going to blow it up just a little bit. So this is the surface of the universe. This is space-time right here. And I'm going to put a couple little dots on here. We'll do a few of them. We'll do 3 dots. Let's let those represent our galaxies, right? Right now, they're pretty close to each other, relative to each other. Let's let the galaxy or the universe expand a little more. So let's blow a little more air into our balloon here. That's some great. Oh, it's kind of hard to tell because I put them a little bit close to the base of the balloon, but you can see that the distance between the galaxies has now changed. They're further apart as I put air into this balloon, as the surface of the universe is expanding, essentially. The galaxies are going to be pushed further and further apart. Let me try this again real quick. I've got 2 galaxies here. You guys see? And now they're much further apart. So as the universe expands away, it drags the galaxies with it. And their velocities relative to each other, the distance that they are changing, increases, right? So that's a little demonstration you can do with a balloon to replicate what the effect of the expansion of the universe is.
Thanks, Amelia.
Okay, and I continue from here. While Amelia had fun inflating balloons,
We'll let
The
Amelia,
point-
we'll let Amelia catch her breath. Dimitrios, we have one question.
yes.
Samuel asks, if the universe is expanding at an accelerating rate, why did Hubble get a linear plot?
Oh, okay. That's also a very good question. In fact, Samuel, this linear plot is applicable only for small distances, up to redshift of approximately 1. If you look at further away galaxies at higher cosmological redshift, then you see some change. The plot is not linear anymore. And that's actually, we know why the universe is accelerating. We look at far away sources like supernovae, and we see changes in this slope that tells you actually that the rate with which the universe increases is accelerating. And that was only discovery made some 20-25 years ago and gained to these people a Nobel Prize in physics, in fact. That was an excellent question. So when you have the expansion of the universe, doesn't mean that when we see galaxies moving away from us, it doesn't mean we are in the center of the universe. It's, as you saw with the balloon, the distance among all the galaxies increases. It's more like baking bread with raisins. You put your dough with the raisins inside, and let's bake our bread. What do you think happens to the raisins when the dough bakes and expands? What happens to the distance between the raisins? In that case, the raisins are galaxies. The bread is the universe, and the raisins are the galaxies. We have some answer, I believe, at the chat.
Yeah, we have a couple of answers. One says it increases, another one says all of them are moving away from each other.
And all of this is correct. That's exactly what is happening.
Distance between the raisins gets larger.
That is absolutely correct. There is no special raisin that is in the center of this bread. They are all spread around, and as the bread expands, all the distances increase. And that's what is happening to the universe. Even more amazing is the fact that as the universe expands, the space itself expands, and the wavelength of light is getting stretched. A galaxy that produces a blue photon much in the past actually appears to us as a red object. The reason is that this photon traveled for billions of years in space, and as space expanded, the wavelength of this light stretched. The wavelength got longer, and today that is arriving to us, it's a red light. Actually, if you want to look at objects that are very far away from us, you have to look in the infrared part of the spectrum at wavelengths that we cannot even see with our own eyes. To do that, we actually need a very cold instrument in the deep space, and a huge one, as a matter of fact. And this is exciting time in astrophysics, because as of last year, we got this infrared eyes in deep space. We got the James Webb telescope. Probably you have seen some of the amazing pictures that the James Webb has taken of galaxies, planets, and other objects. It looks in the infrared part of the spectrum and can discover galaxies at a very large cosmological redshift. A few days ago, there was a publication of this discovery of galaxies at the cosmological redshift of 12 or 13. In that case, the wavelengths of light have been stretched by 12 or 13 times in comparison to those produced by the galaxies. And these are quite red objects. So we have just started this era of discovery. But I will stop here and I will take your questions. Thank you for your attention.
When you say the redshift is 12 or 13 times, I can't even wrap my head around that. That's phenomenal. What great discoveries we are about to see.
Absolutely. These galaxies, we get light from these galaxies when the universe was 300 million years old. Today, the age of the universe is around 14 billion years. So you can imagine the universe very young when these galaxies were already there, and they were actually quite big, substantial galaxies. So we try to wrap our head around how you get galaxies forming so fast and getting so bright. But it also tells us that this telescope, the James Webb, is going to discover many more objects out there.
Dimitrios, if we are at 90 minutes, and I think we have to wrap up, that was a very good presentation. So I would say, I think in the last hour and a half, we've had a good experiment, some good explanations, some good discoveries of our own. I thank you. I thank our TAs for participating, and especially the students that have stuck with us. You've had some great questions. If you have any other, excuse me, if you have any other questions, feel free to email me, and I will try to answer your questions. Nellie is asking, do we have any advice in getting through college as an astrophysics major? Nellie, how about if I have our TAs respond to that question by email? Would that be okay? And we can, if you give us, or maybe into next week, or we have a holiday coming up next week. So give us a little time, and I'll ask our TAs to respond to your question by email.
Yes, there are definitely many good physics and astronomy programs that I can follow so that you become an astrophysicist. It takes good background in mathematics, good physics, and astronomical knowledge, of course. But RTAs will give you a lot of details.
And it takes curiosity. So curiosity and creativity. So,
you all took the first step by coming here and attending this and participating in this event.
It's a good first step. The next good step might be enrolling as an undergrad at Purdue University. We have a great astrophysics department, great faculty, and great support. So we've got some emails in the chat. Any of you can feel free to email the students that have been with us today. All right, let's wrap it up. Thank you all. Thank you everyone for being here. We will see you next time at Saturday Morning Astro at Purdue. Bye-bye.
Bye-bye.